Okay. Okay, so let's start with chapter 7. We're gonna probably finish that today and tomorrow. So this is gonna be, and there will be only just one more chapter, which is chapter number 8 about cointegration. Okay. So now before we go to cointegration, we have to know what an integrated process is. And first off, we're gonna start with the so-called random walk. Okay, so that's gonna be the first thing that we'll consider. So this is going to be the so-called random walk. Okay, so again, but let me just start with here with this chapter. So this is going to be part of the so-called non-stationary processes. Okay, non-stationary processes. Okay, so the first one will be the so-called integrated and transstationary processes. Okay, so this is going to be chapter 7.1. So integrated and transstationary processes. Okay. So again, I mean, I'm not sure whether or not you have read the newsletter, but if you read the newsletter that I have just announced that for next week we don't have lectures. I want to use the time just to talk to you, okay? So you basically have more time before Christmas to prepare for other things. And the final lecture will be just in the first week after Christmas. So you just need to have one final lecture. But I want to make sure that until then you all know what you're going to talk about. Okay, so in terms of your seminar paper. So okay, so I would like to talk to you about the seminar paper, and maybe you can select the study until then, so that just a study for orientation. All right. Now, again, so let's start with the so-called random walk. Okay, so stochastic process is called the random walk. So this is going to be the next definition. So what is a random walk? Okay. So what you have is, for the random walk, okay, so basically you have a stochastic process that can be written or can be expressed as follows. So here you have yt and then yt minus 1 plus the noise. So basically, I mean, you will have this is a special case of an autoregressive process where the coefficient is equal to 0. Okay, so maybe you remember that. So this is going to be the special case. I mean, let me just consider it in this example. So basically you will have that, okay, so let's say y is an autoregressive process, the first order autoregressive process. So this means that yt is equal to a constant plus a times yt minus 1 plus the noise. And let's say if the constant is equal to 0 and a is equal to 1, of course, then the process is going to be a random walk, right? Obviously, right? So this is then, so this means that y is a random walk. So this is just a special case, basically. Now, what you have is that obviously that the random walk is not stationary, because for the random walk to be stationary, or let's say for an autoregressive process, if order 1 to be stationary, remember that the stationary conditions, all roots of the Lac polynomial have to have, let's say, an absolute value which is greater than 1, and this is only true if, let's say, absolute value is less than 1. So which is, of course, obviously the random walk cannot be stationary. Okay, so in this case, random walk cannot be stationary. Okay, so random walk is not stationary. Okay, obviously, right? That's for certain. Okay. Now I mean, we're going to look at certain properties here, but let me just add another process, another definition. So this is going to be the random walk with drift. Okay, so this is going to be the second definition. Okay, so this is going to be a random walk random walk with drift, okay? So in most cases, this is going to be just in a more general case. I mean, in that case, you will have that yt can be written as, I mean, you have the random walk, so this is the regular random walk, yt minus 1 plus the noise at point t, and then you add a constant here, okay? So the constant will be the drift, okay? So basically this is going to be the drift, all right? So that's just going to be it, okay? So again, here just an autoregressive process where the constant is not 0, okay? So let me just add here this to it, okay? So just an example, let's say you have y, okay? So let's say y is an autoregressive process, the first order autoregressive process, basically the same thing. So you have a constant plus a times yt minus 1 plus the noise. And here, of course, you have that y, the constant is not equal to 0, but let's say the coefficient a is equal to 1. So in that case, you have a random walk with drift, okay? So of course y is a random walk with drift, obviously. Okay? This is just going to be. Okay? Now, of course, the process is not stationary, and there are lots of reasons for that. I mean, we're going to look at it a little bit closely, but let's have a look at another representation here of the process. So, I mean, we have already seen, okay, again, so a first order autoregressive process, okay. So if, let's say, y is a first order autoregressive process, then we have probably seen, and you hope you remember that from chapter 3, that the process can be represented as follows. So here you have, let's say, v times, and here you have j is equal to 0 till t minus 1 of a to the power of j, and then plus a to the power of t times y 0. So that was the starting value, and then you had that. I mean, you have different realizations here of the noise, so j is equal to 0 till t minus 1 of a to the power of j times epsilon t minus j. So that was the representation that we were looking at. Maybe you remember this from chapter 3. I did this, or I derived this formula here from using induction. And the reason for that is being that here using this representation, stationarity and other properties can be also can be basically better examined, okay? And that's why I was doing this. And so therefore, I mean, you just develop the formula again. Now, let's say if you have a random walk, okay? So if you have a random walk here, then this is what you would basically do. Then you would get, so let's say if, and this is going to be the first case, okay? So let's say let y be a random walk. So if y is a random walk, then you would basically get that, I mean, v is equal to 0 and a is equal to 1. So if it's say v is equal to 0 and a is equal to 1, then basically this process here, or this representation, simplifies to the following expression. So here you have the starting value, and then plus, okay, so all coefficients and whatsoever cancel out, so basically you would just generate here the following expression. So you could start at j is equal to 0 to t minus 1, or what you could do is you could start at t is equal to 1, and or let's keep that first, okay, so t is equal to 0, j is equal to 0, sorry, and t minus 1 of epsilon t minus j, or basically you could use that, you just rearrange this, because the first one of this expression is going to be epsilon t, the second one is going to be epsilon t minus 1, the third one is going to be epsilon t minus 2, etc., etc. So you could also change that. You could also start at g is equal to 1 and stop at t, and then you have the similar thing, so then you will have just epsilon J, just for the rearrangement. Okay, so there is no difference here between the two representations. Again, I hope you understand this. Okay, so this is going to be epsilon 1, epsilon 2, epsilon 3, and so forth and so forth. And then you have epsilon t is the last one. And here you start with epsilon t. Okay, epsilon t minus 1 and epsilon t minus 2, and then the final one is going to be epsilon 1. So that's just a different order. Okay, you see this, guys? Okay, so here you have, this is going to be, first one is epsilon t and then plus epsilon t minus 1 and so forth, and then this is going to be epsilon 1. And here you start with epsilon 1, epsilon 2, etc., etc., and then you have epsilon t. So that's going to be equal. Okay, so this is just another rearrangement here. All right. Okay. Now, if this is going to be the first case, and then the second case, all right. So the random walk with drift. Okay. So let's say y is a random walk with drift. That's going to be the second case. So random walk with drift. Okay. Now, here in this case, you will have that v is not equal to 0 and a is equal to 1. Okay, so that's reminding us here in a special case. Now, if v is not equal to 0, okay, so this expression becomes familiar with that one. Okay, so there's no difference here for that. Let me just rearrange that here. So you're going to have v. Okay, so here in this case, or that this is not v, but this is just here another constant, let's say delta. Okay, I mean delta is not equal to 0, or I mean basically here you would have that v is equal to delta here, of course. So I mean this is just 0, just a representation. Okay, let me just add this here, so that probably that the constant here of this previous representation should be equal to delta, so delta would be the drift here of the random walk. So in that case, this representation v times the sum here becomes the following. So you have v times the sum, and since a is equal to 1, you have 1 to the power of j, right, which is of course obviously equal to 1, of course. So it's j starting at 0 at t minus 1. Okay, and you can add j here, but you don't really have to because it doesn't change. And you're going to have the starting value. Okay, so a to the power of t times y0, and of course if a is equal to 1, then you have a to the power of 1 is just equal to 1, so you have just the starting value, of course. Okay, so the starting value, and then this thing, okay, again this thing changes to that one. So, and that is something that we've already seen, so you don't need to look at that anymore. So again, so j is equal to 1 and t, so here you have epsilon j, of course, right? So that's going to be, now let's simplify this expression, okay, because let's say the constant is equal to delta, so you're going to have that this is going to be equal to delta, and if you add 1, so you have 1 plus 1 plus 1 plus 1 and so forth. Okay, so from j is equal to 0 then to t minus 1, then you have a t times in there, you understand? So this is going to be t times 1, so you have, of course, so delta times t plus the starting value plus the sum of the noises. Okay, so here you have the sum of the noises, and this is the linear trend here, obviously, in the data. Okay, I mean in this case, obviously. Okay, so this is just another representation here of the process, and again looking at this or these representations, then it will basically have that you could examine the expectation and the variance here of the process as well. Okay, so that's what you're going to do. Okay, now let's look at the following expressions. Of course, I mean, if let's say you have that I mean, if delta is equal to 0, then of course the expectation is going to be the expectation here of y0. Okay, so here in this case, and that's going to be obvious. So more interesting is the variance here of the process. Okay, so how does the variance evolve here for this process? Okay, so let's say variance of yt. Okay, now we assume that, I mean, before we go into this, we assume that the starting value is already fixed. Okay, so you have a y0 is going to be equal to c almost surely. Okay, so it's going to be a constant with probability 1. So if you look at the variance here of that, then you would basically have that this is going to be, let me just start here. So this is going to be delta times t plus y0 times the sum of the noises. Okay. And basically, since this is a constant, let's say almost surely, that it has no variance. Okay, so the variance does not depend on an additive constant. I hope you still remember that. So you're going to have just the variance of the sum. Okay, so the variance here of the sum, which, of course, since the noise is independent, is going to be equal to the sum of the variances. Okay, that's for certain. That's for sure. Okay, I think I missed something here. I'm not sure whether or not. Okay, no. This is no. I was thinking about here this expression. Okay. Anyways. No. Everything is fine. Everything is fine. No. This is fine. The variance here of the sum is going to be the same.
You multiplied y0 times the sum.
Yes.
Plus. Now it's times instead of time.
No. Yeah. Okay, that was the problem here. Yes, of course. Sorry, guys. Okay, so they have the starting value plus the sum of the noises. Yes, I was a little bit confused because of that. Okay, because I wanted to drag that out, but I didn't know what to do. Okay, now here you have the variance here of the sum, and then of course the sum of the variances, because this is going to be equal. Okay, so the variance of the sum is equal to the sum of the variances if the noises are independent, and by assumption it is, so it's going to be the case. And of course you have the noise, the variance here of the noise is always going to be sigma squared, right? And see, you have that t times, so this is going to be equal to t times sigma squared. Okay, so there is a linear dependency in the variance. Okay, again, so that's basically illustrates that the process is not stationary. Okay, obviously it cannot be the case. Okay, now what about the covariance? Okay, so the autocorrelation. Okay, so the covariance of yt and yt plus h, where basically h is greater than 0. Okay, now for the covariance you need to consider just basically, the covariance does not depend on the additive expressions either. Okay, again, so the covariance does not depend here on this expression. It's not there. So it only depends on basically the sum. It's not there anymore. So what you would consider basically only is that the sum here of the noises from j is equal to 1 till t, okay? And here you have the noises from j is equal to 1 till t plus h, because these are only the two time lags, okay? Again, the additive constants don't play a role here in this expression, okay? We already seen this. Now, in the first lecture, I was talking about the covariances of sums, right? So the covariances of sum are only playing the role if basically the noises correlate to each other. Now, since the noises are independent from this time on, okay, so you only have, let me just split that up here a little bit. So this is going to be the first one is being j is equal to 1 until t, and the second one, I'm going to split this up. So the first one was j is equal to 1 until t of the noise, and then the second part, j is equal to t plus 1 till t plus h. There you go. This is it. So this is aj, right? Now, this expression, okay, these two are correlating to each other because the covariance of that is going to be the variance. Okay? And of course, this expression or any of the noises that are here do not correlate of the noises that you see here in the first expression. All right? So none of these noises correlate to each other. So then, of course, and you have the covariance of the two, and the covariance of the two is going to be, of course, the variance of the sum. And the variance of the sum is already t times sigma squared. So that's basically what you would obtain. So this is going to be t times sigma squared. So as you can see that the autocovariance is also time dependent as well. Okay, I mean, but they have to add that h must be greater than 0, because if h is not greater than 0, then this split does not hold, obviously. So then you would get something else. Okay? Does that make sense, guys? So basically both the autocovariance and the variance here of the process is time dependent. I mean, the expectation can be time dependent here. Okay, so the expectation here of the process only depends on time. If, let's say, if you have a trains, you have a random walk with drift, okay? But if you don't, then basically the expectation is equal to the expectation of the starting value, which is a constant, of course, because the noises have all the expectations 0. Okay, so that's not very interesting. Okay, is this something that is clear? Okay. Now, of course, we look at some certain properties. Okay, so, but obviously the random walk is not stationary. Okay, because I mean the variance is time dependent, so it cannot be the stationary, but the autocovariance is also time dependent here. Okay, but most importantly the variance. Okay, so the variance of the process is time dependent. Basically, it's linear in time, so the random walk is not stationary. Okay, now let's have a look at certain properties. Okay, so basically, I mean, this is going to be summarized by the following lemma. So I will add this here also. Okay, so suppose that you have, okay, so y is a random walk. Okay, no drift here. Okay, but then we have the following. So then basically the expectation here of the following sum. So what you do is, okay, so here you have, let's say, I add up the process, so starting at a point t is equal to 1, and then you have capital T. And what I'm doing is I'm taking the sum of the squares. Okay, so I'm taking the sum of the squares, and the sum of the squares is going to be equal to the following expression, namely sigma squared, which is the variance of the noise, times capital T times t plus 1 divided by 2. Okay, so as you can see that the empirical variance will be converging to infinity, as you will see that here is a result. Okay, because that's what basically this proposition is about. Let me just illustrate this why that is. Okay, because this is very important. Okay, so again, so the expectation here of the sum of the squares is going to be equal to the sum of the expectations, first off. Okay, so first off you have the sum of the expectations, so I'm taking the sum of the expectations. So this is going to be the sum of the expectations. And of course you have the squares. Now the expectation of the square, I mean, since you have basically that the variance of a certain random variable is equal to the expectation of the square minus the square of the expectations, okay, basically you would get that this expression is equal to the following. So basically you can replace the expectation of the square by the variance of the corresponding random variable plus the square of the expectation. So here you have the variance of the random walk plus the square of the expectations of the random walk. Okay, so here you have t is equal to 1 until capital T, of course. Okay, now if you assume that basically the process starts at 0 almost surely, okay, then basically this expression cancels out, because this is equal to, and that you would have here, this is equal to the expectation of the starting value. Now, of course, the expectation of the starting value, if you assume that the starting value starts at 0 almost surely without loss of generality, okay, so in this case we assume that the starting value starts at 0 almost surely, okay, meaning that with probability 1 without loss of generality, of course, loss of generality, then basically you would have is that the variance here, or this expression, the expectation here of the sum of the squares, okay, so the expectations here of the sum of the squares is going to be equal to this expression, because this cancels out, okay, so in this case this is going to be equal to this expression only. Now what's going to be the variance here of yt? Now the variance of yt is equal to the variance of the random walk. We just had it, and this is going to be equal to sigma squared times t, or t times sigma squared, obviously. Okay? And this is equal to sigma squared times the sum of all numbers starting at 1 until capital T. Okay? Now I'm not sure whether or not you remember this formula, but the sum of all numbers from 1 to capital T is going to be equal to t times t plus 1 divided by 2. You remember this formula? I mean, you do, but what about the rest? You do that too? Okay? No, you don't? I mean, let me just illustrate this, how it works, okay? So here 1 plus 2 plus 3 plus blah, 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 plus capital T, okay? This is the sum that we have here, okay? Now what you do is you take the pairs, okay? So first off, you start with this one. 1 plus t is equal to t plus 1, right? So then you take 2 and here before that t minus 1. So 2 plus t minus 1 equals 1 plus t as well. Or t plus 1, let's say. Okay, so, and then this is going to be the third pair, so the third pair is going to be here, right? And the sum of the pairs is always going to be t plus 1. Okay, so the sum of the pairs is going to be always t plus 1, no matter what. Okay, you understand?
Yeah.
Now, the question is, how many pairs do you have? If you have, let's say, from 1 to 100, then you have 50 pairs. Okay? If you have, let's say, 1 to 1000, then you have 500 pairs. So this is the sum of the pairs times the pair times the number of the pairs. So this is going to be t over 2. Okay, obviously. So that's going to be it. So that's why it's you have this expression. Okay, you don't have to know this for the exam, guys. Don't worry. Okay, I'm just adding here this to it. Okay, but don't worry about that. So you don't have to have like extra formulas and stuff. Okay, none of that. Okay. Now, what about the? I mean, what's the problem here with this? Okay, now basically, I mean, if you look at the expectation here of the square minus the square of the expectation. Okay, so basically this illustrates that. Okay, so this expression as, let's say, t converges to infinity, converges to infinity almost surely. Okay, so if you look at the empirical variance, okay, so because that's okay, I will delete this here. Okay, and since the square here is has a convergence rate which is quite large. Okay, so even if you divide this by capital T, okay, so then this will converge to infinity almost surely. So this implies here, let me just summarize that, okay, so that the empirical variance, and I call this gamma, we call this gamma, right? So that was gamma squared of the process y. Again, this was the empirical variance. Okay, and this was 1 over t times the sum of yt minus the expectation, okay, which is the arithmetic mean in most cases. So here t is equal to 1 to t. Now, this converges to infinity almost surely. Okay, so this converges to infinity almost surely, okay, as t approaches infinity. Okay, so basically that the empirical variance of the process explodes. Okay, so estimation of the variance is not possible. Okay, so hence the estimation of the variance, okay, is not possible. Okay, so there is no way to basically to estimate the variance here of the random walk. Okay, and there is also a second property regarding this, basically, and this will mean that the covariance or the autocorrelations will converge in probability to 1. Okay, so this is the other, that's the other property that, you know, integrated, I mean, this will be the random walk, so these so-called integrated processes will have. Okay, and I will add this here. All right, so this is going to be the second problem here regarding this issue. So the problem here is that the empirical autocorrelation, the empirical autocorrelation of the process with time lag h, okay, which is again the following. Okay, so here down there you have the variance. Okay, so here your yt minus y bar squared. Okay, I mean the sum here starts at 1 and stops at capital T. Okay, I don't have much space, so I use that a little bit more properly. Okay, so 1 over t cancels out, so we just dismiss that. And here in the numerator you have t times the autocovariance on the empirical one. So you have yt minus y bar times, okay, so let me just do this here again, so because that's not appropriate. Okay, so here you have the sum starting at t is equal to 1 and yt times minus yt bar, y bar, sorry, times yt plus h, okay, minus y bar. Okay, so here you have the empirical, so t times empirical autocovariance. Now here this sum stops at capital T minus h, of course, because we don't have any more expressions. Now this thing, this is the empirical autocorrelation, will converge in probability to 1 as basically the time approaches infinity. Okay, so for the estimation. So if you have more if you include more observations into the sample, then this expression will converge to 1, because the two here, okay, so that one times that one will become basically yt minus squared almost surely here in most cases, because you know the time lag is going to be neglected here. So you have t plus h here. Okay, so if you fix the time lag and you increase the sample size to estimate the autocorrelation, then the autocorrelation will converge to 1 falsely. I mean, basically you would conclude that the process autocorrelates here. Okay, and that doesn't make sense. Okay, perfect linear relationship between two observations here for the time lag, no way, that's not going to be. Okay, I mean there is randomness in the process. Okay, but this is a property that these things have. Okay, so if you perform basically if you perform a regression, okay, on a current observation of the process and the past, okay, then you would find that the correlation is, okay, so the correlation will be close to 1, obviously. So basically meaning that the test statistic of the regression will be significant with probability 1. Now, this is something that you cannot do, okay? And again, so you have to be careful. So if you have a random walk, that this is something that can happen to you. So you have to make sure that you don't have a random walk, because otherwise the corresponding Gaussian and autocorrelations and so forth do not make any sense, okay? That's a process, that's a problem. Okay, now we define the so-called integrated processes of order 1, and this is going to be the first order integrated processes. I'm sorry, I didn't know what I was pushing here. Okay, and let me just, okay, you understand the point? So this is a problem, and this is a direct consequence here, since the variance converges to infinity. This expression will converge to that expression as capital T increases, and as capital T increases, then you have that basically that. If the two are becoming similar, more similar in probability, then the process or the corresponding autocorrelation will be converging to 1 as the sample size increases. Now, that doesn't make sense in a regular case, of course. All right. So now we need to define the following process. Okay. So suppose that this is going to be the next definition. Okay, so let's say we have we have a stochastic process. Okay, so A is a stationary process with a finite long-run variance. Okay, remember the long-run variance. Okay, so what was the long-run variance? So I will add this here. So the notation was omega. Okay, and I will use the process here itself. So this is going to be, or was, the variance of the process. Okay, plus the total sum of the covariances, so 2 times the total sum of all autocovariances. Okay, so here you have the covariance of ET, okay, and here you have ET plus H, okay, and you take the sum from t is equal to 1 to plus infinity, so you sum up everything, and you find that this is going to be finite. Okay. Now, if the long-run variance is finite and the process is stationary, then basically this thing, okay, is called integrated process of order 0. Of order 0. Okay. What you also need to have is that the long-run variance is also greater than 0. Okay. So first off, the long-run variance has to be finite, and if, let's say, the long-run variance is greater than 0, then basically the process is called integrated process of order 0. Now, I will explain what order 0 means. Order 0 has nothing to do with basically that being that. This is just a direct consequence, but it does not relate directly to the long-run variance. Okay, so the long-run variance is not where the name is coming from. I will explain this later on. Okay, now if you do the following, okay, so if you define, okay, so that's going to be the first definition. If, let's say, you have another process which is a sum, okay, a sum of these integrated 0 processes, okay, so you would take basically, I call this J here, this summation index, all right, And this looks quite similar to a random walk, as you can see. So where basically you will sum up, okay, these integrated or processes of order 1. Then if you have that, then the process is called integrated of order 1. Okay, so then y is called integrated process of order 1. Okay, so these are the two that we distinguish. Okay, and then the notation here is as follows. So here you have y, so this is how we denote this, and then you have tilde, then you have capital I denoting for integrated, and that's how you would do it. Okay. Okay. You see? Now, there are different cases here for that. Okay, I will explain what order 1 and order 0 mean. Okay, but we need a little bit of time for this and need to accept this. There is also a third case, let's say, and then if, and because that was the case that the stationary process with 0 mean. I forgot to add this here. And okay, let's say, and I will continue here. So the integrated process one, if, let's say, the mean, okay, so the expectation here, if the expectation of the process E is going to be 0, okay? Right? So that is something that we also need to have, okay? Again, so the process is stationary, so the expectation does not depend on time, but in particular, if, let's say, the expectation is 0, then of course this can be written like that. And if the expectation is not zero, maybe with a random walk with drift, okay? So if, let's say, okay, the expectation here of the process ET is equal to delta, okay? Oh, that's the notation that I use. And you have that basically that yt is going to be equal to the sum here of these processes. Now, in that case, you have that this is going to be equal to delta times t, as in the previous section, plus the sum of these stationary integrated of order 0 process. Okay, so you have here the observations when j is equal to 0 to t. Okay, just as this has been the case for the random walk. Okay, then basically then you'll have, okay, so then y is called integrated, okay, of order 1 with drift. So basically the same thing. Let's just consider some examples, okay? But let me just see where the, okay, yes?
What is the second part of if expectation of ET is 0?
Okay, so here in this case, I mean, let me just give you an example. So just to illustrate that, so called integrated of order 1 with drift. Okay, let me just give you an example, so then you understand this. Okay, the definition becomes clear from the example. I mean, suppose basically that you have the following. Okay, so suppose, let's say, for instance, ET is equal to, and then here you have basically delta, okay, delta plus the noise, okay? So epsilon t is a white noise, okay? So epsilon t is a white noise. okay? And suppose that the white noise has a variance, okay? So with variance sigma squared, okay? I'm just waiting for you. Now let me just, let that just be the first example that we consider. Okay? Now what's going to be the expectation here of this? Okay, so what's going to be the expectation here of the process? That's easy. So the expectation of the sum is going to be the sum of the expectations, right? Now the sum of the expectations, okay, so here they have a constant. So expectation of a constant is a constant itself. And the expectation here of the noise is going to be 0. So that's going to be the expectation here of the process, right? And what's going to be the variance of ET? The variance is going to be, the variance of the sum is the sum of the variance, but of course this is a constant, so it doesn't depend on that. So this is going to be sigma squared, okay? And since, you know, the noises are independent, so then basically that the autocovariance is also going to be 0. So the autocovariance is 0. So this means that the process is going to be stationary, right? The process is stationary. You remember that? Okay? Is this clear? Okay, so the autocovariances, okay, let me just here add this to it, are going to be 0 for h being greater than 0. Okay? So the process is stationary. Okay? You understand? Okay, so this means that AT is stationary. Okay? Now, question. Is this gonna be also a integrated process of order 0? Let's check it out. So for that, what do we have to have? We have to have that the long run variance of the process is positive and greater than 0. Okay? Let's check it out if that's going to be the case. Okay? So what's going to be the long run variance here of the process? I mean, let's have a look at this. I mean, that's the long run variance here, the definition is going to be here. So this is going to be the variance of the process plus 2 times the covariance. Okay? Now the covariances are also going to be 0. So if the autocovariance is going to be 0, then this is going to be 0. So then you have the long run variance, which is going to be equal to and the variance here of the process, right? So this is just going to be the variance here of the process. All right? And so therefore, okay, what you would, okay, so this is going to be stationary, and what you would look at the long run variance here of the process, okay, so the long run variance, maybe you also remember this expression, okay, so this is going to be the variance here, okay, plus 2 times the autocovariance, okay. I will just add this here, okay. So the covariance of ET and ET plus H is going to be equal to sigma squared, okay. I will write this down again. I don't have much space here, okay. So maybe you can check it out, okay. So, I mean, the long run variance, okay, the long run variance here of the process is going to be equal to the variance plus 2 times the autocovariance, okay? ET plus H, okay? Now, of course, this is going to be equal to sigma squared because the autocovariances are equal to 0, okay? And that is greater than 0. Right? So then the process is of course integrated of order 1. You understand? Okay? So this means that is integrated of order 0. Okay? Or E is integrated of order 0. You understand? Okay? Right? So that's the first thing. Now, if you sum this up, okay, and we had this, if you sum it up, okay, so let's define, let's say, another process. We define yt, and by summing it up, okay, so summing up everything, yeah. What you-
The longer variance, does it have to be finite or?
It has to be finite. Yes, it is fine, but it is finite. So it's finite. Okay, so
What if
sigma
it's
squared.
equal to 0?
Yes, it has to be finite.
What
Yes.
if it is equal to 0?
No, it's greater than 0.
I mean, what if?
The longer variance.
Yeah.
I mean, because the variance here of that is going to be. I mean, we had this in the previous
The
section.
definition says that it has to be finite. I mean, so
No, it says the following. So it's called integrated of order 0. I think maybe I missed that. Okay, it's integrated of order 0 if the variance. Here you have if the variance.
the longer variance.
Yes, if the longer variance is greater than 0. So it's not just only that the process must be stationary. It must be also that the corresponding thing is going to be also greater than 0. Okay. All right. Now let's have a look. I mean, and that's how you would sum up basically the process as well. Okay, so it does basically what you would have is going to be the same thing. Okay, so I'm not going to focus on that, but I'm going to give you another example where basically that you will have a process which is stationary, but not integrated of order 1. And let me just give you another example here. So for instance, ET, let's say, should be equal to epsilon t minus 1. Maybe you remember this. This is a moving average process, okay, of order 1. So epsilon t is a moving average process. Okay, so the first order moving average process, obviously. Okay? You remember this? Okay? You have seen the representations here of that. Now, moving average process is stationary. Always. Okay? So hence, E is stationary. Okay? However, guys, and maybe you remember this, however, the longer variance of the process, and we have seen this quite often, okay, is equal to sigma squared times the lag polynomial b at point 1.